All right, so welcome to the next video here. And so in this video, we're going to talk about how to represent areas using first some notation that we are very familiar with from pre-calculus, and then new notation to help us out with after that. So to start out with here, I have a function, that red line, red curve you see there, that's f. And so we're going to be interested in finding or estimating the area under the curve of f from a to b, where those are just some x values, okay? And specifically, we're going to try to represent it using right endpoints, okay? So typically, we sort of divide it up, and they tell us, like in the problem, like, oh, divide it up into, 6 rectangles, 12 rectangles, 3 rectangles. Here, it's not as descript as perhaps you would expect. So I'm just going to start drawing in rectangles. And then I'm just going to go ahead and fast forward a bit and get to the end here. So that dot, dot, dot in there is ambiguous, because what I'm trying to sort of show here is that, like, there are some number of rectangles. Could be 3, could be 100, could be 12, could be 1,000,000. So I'm just sort of drawing this in like this. And then you can even label the different x values, like this one could be like, actually I don't want to do that. I think that's a bad idea. Yeah, we're not going to do that. But what I do want to do is actually sort of say, like, FYI, there are n number of rectangles here. So I'm going to define n as being the number of rectangles that we're using here. And if you're like, wait a minute, I count 7 rectangles or whatever, just remember, like, this dot, dot, dot means that, like, there are more in here. And so we're going to use right endpoints. So I'm going to go ahead and start actually drawing in the rectangles. The choice of endpoints actually for this is not that important. The right actually makes the indices, that's the plural of index, for our summation notation a lot nicer. But you can still do it, like, we usually start at 1 with our summation. And so this will ensure that we start at 1, but, ultimately you don't have to. Okay, so I'm going to go ahead and start thinking about how I might represent this. So usually I sort of take it, rectangle by rectangle when I'm trying to fill this out. So I want to represent the area of each rectangle. So I'll start with just this first rectangle right here, like, okay, let's find the area of it. And I'm going to start writing down how to represent that. So the area, A, is approximately. So the height of this rectangle is based off of that point right there for our function f. Here's the thing is, I don't actually know what that input value is right there. It's a bit bigger than a. I just don't have the number to go with it. Well, this is where talking about n number of rectangles is helpful, because what I want is that this length, this input value here, is a plus whatever that length is. So I know that the height of my triangle, or my rectangle, is going to be f of a plus what, though? Like, how much is that? Is it a distance of 1? Is it a distance of a fifth? Is it a distance of 1/1,000,000th? Well, since we're dealing with just generic letters here, you're not going to be able to attach an actual number to it. But you can use the things we've signed up here so far to come up with that distance. So that distance, it's going to be the same distance for every single one of these. I'm not going to get all weird with it and create different distance rectangles. And so what is that distance? Well, it's some number of chunks. Well, n number of chunks that span the difference from A to B. Okay, so all the words I just used actually do talk about that sort of idea. So let's go ahead actually, and for now, let's take a moment to think about, all right, that change in, I'm going to go ahead and call it delta x. That delta x right there, that delta x is the distance from A to B, so B minus A, all divided by the number of groups that's in groups. So each time I click over, I'm clicking over a B minus A all divided by N. So B minus A, that's that distance, and then chunked up into N number of rectangles. Cool, so I can go ahead and come over here and go B minus A all over N. And now I have actually what that base length is for my rectangles as well. The base length of my rectangle is B minus A all over N, so I'll go ahead and write that in over here too. So that's the usual setup, base times height of each of my rectangles. Okay, well, let's keep going here. So plus rectangle number 2. So now I want to think about this. Well, that base length is the same, so it's B minus A over N times, and then the height is going to be based off of that x value there. So f of, well, this time it's A and then 2 clicks over. So 2 of these B minus A over N. So A plus 2 B minus A over N. All right, and let's keep going. So boom, 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 boom. The third one, I'm starting to see the pattern. So the base, still the same. And then the height, f of A plus, and it's going to be 1, 2, 3 clicks over. So 3 B minus A over N. All right, I'm starting to get bored a little bit. So I'm just going to fast forward here to the very end. Plus, we'll write that plus down below here, plus, and then we're going to come all the way to the very last one here. So the base length is the same, B minus A over N. The height is determined by, so just graphically right here I can see that like f of B is what it's supposed to be here. But I also want to see if I've started to recognize the pattern well enough. So it's going to be f of A plus, well, let's check this out. So if I kept going, I'd have to click over n number of times to get to here. So this would be n times B minus A over N. And let's do a quick sanity check here. So n being multiplied and divided, those will divide to 1. That'll get me A plus B minus A. Cool, so A minus A, that's 0, leaving me with just B. So this inside the parentheses is equivalent to just B, which makes sense because we're using the right endpoint over here to plug in to find the height. So it makes sense. I always like to do that. All right, so this is a little bit too much. So what I want to do is I want to try to shorten this up using summation notation or series notation, using the sigma, the big old capital Greek S. And so this actually brings us to a definition. And it's not really a definition as much as it is like just notation that has a name. So this particular thing is called a Riemann sum. So what's written above is a Riemann sum, technically, but typically when you see a Riemann sum, it is written in a form that is using summation notation. So let's see what we could do here with the summation notation. So the area is approximately equal to the sum of, I love drawing those are fun. The sum of, well, let's take a look. So we're adding up these things every single time, and the structure of each of those terms is very identical to each other. They always have a B minus A over N. That's definitely part of it. And then it's being multiplied by f of, and it's always A plus, and then it's some sort of factor of b minus a over n. So the only thing that changes from term to term is what is the coefficient to the b minus a over n. And so you can represent it with a lot of different things. I'll call it I for index. So that I is going to be the thing that changes. And I need to now define over here where it will start and where it will end. So I will start at, up here, you can see that it starts at 1. And it continues along until you get to the nth iteration. And there you have it. That is a Riemann sum. So that's for right endpoints. If we were to go for left endpoints, well, then you would start at A. The easiest thing to do would just to start at 0, and you'd have to end at n minus 1. If you want to do midpoints, it's a little bit different. And the structure, of course, would be quite a bit different if you wanted to use trapezoids. So this is the way to do it. So like computers, if you wanted to try to figure out, estimate the area under the curve, you can plug in, you can tell the computer like, all right, here's my function, so boom, there. Here's where I'm starting and ending, there's my A and my B. I want this number of rectangles, and so those things will all be plugged in and it'll figure it out for you. So if you are interested in programming, you do Java or Python or something like that, building a program to do this is not very difficult at all, as long as you understand like the syntax of the language. So this is a good way to find what we call like sort of a numerical area, an estimated area under the curve. Because oftentimes, as soon as you make in, 1,000, 1,000,000, 10 million, like that's good enough for most things in the world. Now, of course, if we wanted to be exact, because this is just approximating area, we would want to use something called an integral. So how did the integral come about? Well, from the Riemann sum. So if we wanted the Riemann sum to not be an approximation, but instead an exact value for the area under this curve, well, we would have to think about how, like, a lot of these things are pretty stationary. The only thing we have control over is this, like how many rectangles do you want to do? And so we've talked about in class that the more rectangles, the more accurate. And theoretically, to be as accurate as possible, you should use an infinite number of rectangles. Obviously, into like Java and Python, your computers and stuff like that, you can't plug in infinity for n. So how do you sort of fake it out? Well, that's where we come back to limits here. So if we wanted to find the exact area under the curve, so A equals exactly, well, we would want to take our Riemann sum that we have. And we'd want to use it cleverly. We would want to then use this and do the limit of the Riemann sum and make n head to infinity. There are other, sort of ways where you can write infinity up here, which I think is not like quite proper. I know you learned it in pre-calculus, but that was just because like limits were sort of also kind of new. So we could fake it out and be like, all right, cool, this thing, except for make n go to infinity. Now, sometimes there are like really clever formulas that we have that can allow us to figure this out, and sometimes there aren't. So, so if we wanted to find the exact area under the curve every time, we would have to do this. The limit as n approaches infinity of the summation from 1 to n up. It's a lot of words. It's a mouthful for sure. So somebody that was much lazier than you or I decided to come up with a different symbol, okay? And they called this the integral. Oh boy, I can spell. Integral. Integral. Yikes. Okay, well, I-N-T-E-G-R-A-L. I started spelling integer, and so I got bad there. Here, I'm just going to do it again. The integral. There we go. So the integral. The integral sort of takes all the ideas here and just like jams them close together here. So what does it do? Well, it does this to start out with. So the exact area under the curve can be represented as that symbol right there is the integral symbol. I'm guessing it's sort of like a fancy looking S, because S, like this, stands for sum. This is also sort of standing for sum. So this, from A to B, so we're interested in the sum from A to B of f of x, that's the function we're looking under, times dx. Boom! There you go. This in blue up here is equivalent to this right here. Much shorter, much closer to like being able to write it a lot. So yeah, let's sort of see some mirrors here. So this whole part here, the integral symbol, is sort of like combining together all of this, but also like the B's and the A's as well, sort of like taking those into account. So like there's a lot going on with just that little symbol. It's saying, hey, this is the limits as n goes to infinity. So this is saying like infinite number of rectangles from A to B. And then here, the f of x, that can be sort of compared with this part here. That's sort of like your f of x, f of something, your stuff that's going in there. And then your dx, dx, well, we've seen something sort of similar to that up here, your delta x. So in this case, like delta x, we as sort of a community have decided like delta x means like a big change, you know? So like if n is some number, that's a big change. If we decided to call it dx, little dx, we're saying this is a very tiny change, which makes sense because we're thinking about n going to infinity. So that lines up with this idea here, the base length. So dx, these are all little delta x's, but as n goes to infinity, they become very tiny delta x's, and somebody long ago decided to be cute and say, cool, it's little dx. That's what we're going to call it. So there you have it. So how do you sort of generally represent it? There it is. That was sort of our first ideas as human beings. How do you do it? And then somebody decided, let's take the limits. And then somebody later on was like, that's too much to write. Could we maybe do something better? And they did. And it all has the same information. You got your height, you got your base length, you're doing a sum between A and B. So we're going to work with all of these notations next class. Be sure to take the survey at the end here so that way we can see what sort of questions you have. Thanks.